Okay, so here's the last and final chapter.
Oh, wow.
Oh,
Which is kind
man.
of cool. If you think about it, we basically got through this entire book.
Really?
Really?
We skipped a couple.
Wait,
It's pretty much all the way through.
Other chapters you skipped go beyond the
So,
Negative.
one of the things,
On the AP test.
No, this is like.
huh?
Other chapters you skipped like divination go beyond the AP test.
So, one of the things that made this whole concept of figuring out what was happening in the nucleus incredibly difficult is that you have two problems. Number one, the nucleus is exceptionally small, so you really can't look at it. And the other problem is that it isn't like we can get a nucleus and dissect it like we can a frog or something and go, oh, let's take a pair of tweezers
Biology.
and let's pull off a number of protons and a certain number of neutrons, and we'll just do that. So there was the two biggest problems that you faced. And the neutrons created their own unique challenge because of the fact that, as you know, neutrons don't interact with electric or magnetic fields because they don't have a charge. They're massive, but they don't interact with anything. The other problem with neutrons is that you don't have neutrons just floating around. It's like, hey, we need some neutrons. Oh, let me go back to the storeroom and I'll grab a bottle of neutrons and I'll just shake some out. Oh, okay, hey, here's some neutrons floating around. So what they began to graph is this line. It's called the line of stability. And up to, especially once you get up to about oxygen and past that, for the most part, and the bottom axis is the number of protons, the y-axis is the number of neutrons. It is not the mass number on the y-axis, it's the number of neutrons. So at the beginning of this graph, you have a one-to-one slope. So the classic example of this is like carbon. So your typical carbon atom, the most abundant isotope of carbon, has 6 protons and it has 6 neutrons. Helium, 2 protons, 2 neutrons. Nitrogen, 7 and 7. Okay? But after that, what they found is that the number of neutrons actually increases at a faster rate than the number of protons did. So as that nucleus gets more and more stable or bigger, you need more and more neutrons to keep this thing stable. And that's basically the role of the neutron. How do you maintain the stability? Because if you just try and smash together a whole bunch of protons, it's not going to be stable. So one of the cool things about our universe is that we have neutrons. The universe just didn't say, hey, we're just going to make charged particles positive and negative charged particles. It could have. We wouldn't be here. Thankfully, our universe decided, hey, we need some neutrons as well to kind of maintain some stability. We didn't gain anything from it, but we're happy that we did. So what happens is that you get this line of stability. This is literally what it's called, this line of stability. So once you get past a certain point, this line curves up. So if you're trying to figure out a potential element, let's say that you think, oh, hey, we want to make a nucleus that has 35 neutrons and 14 protons. Hey, let's see if this is a possibility. So if you come over here where you have 14 protons, and you're way up here with 35 neutrons, that isn't on the line of stability. And basically, if this isotope doesn't fall within that line of stability, it's not going to work. We can't make it. It's not going to be stable, right? So what the line of stability basically does is give you a visual representation that says, okay, what has to happen to make this thing stable? Now, next part. This is where the math is a little bit. This is what's known as binding energy. So the binding energy is the energy that's released if you tear apart a nucleus, or the energy that you have to put into it to build a nucleus. Now, going to need back here on appendix A3, this is going to become your friend. So up to this point in time, if you look on your chart and your masses, the mass of a proton and the mass of a neutron were listed as the same value. Okay? And for most calculations, that works. However, if you come back over here on this table A3, and you're going to need these numbers. So the mass of a neutron is 1.008665 atomic mass units. And the mass of a proton, which is listed as just a hydrogen atom, is 1.007825 atomic mass units. You're going to need these numbers, okay? Now, let's talk about the history of atomic mass units, okay? Atomic mass units came from the idea that when they were trying to figure out the origin of the periodic table, they used to arrange the elements based upon two things, chemical properties and relative atomic mass. They use carbon as the baseline element, mainly because of the fact that it's really simple to find and produce just simple carbon. Literally, if you ever want to do this, I don't recommend it because it makes a bit of a mess. But if you have a typical candle that's burning, and you put just like a glass bowl above that, what you're going to see is a layer of black soot that is forming on the bottom of that bowl. That's elemental carbon. Okay? If you're a chef and you want to make elemental carbon, take some green beans and put them in the oven and bake them to death at a high temperature. They're going to turn black. Okay? You have produced elemental carbon. So this is one of the quirky things that they got lucky on. So they use carbon-12 as the baseline because it's very easy in different labs around the world to produce elemental carbon. Burn a candle, bake a green bean. Then what they said, okay, this is our baseline. They called that 12. They had no concept of protons and neutrons, didn't know anything about it. They just got lucky. And they said, hey, we're going to call this 12. But then a hydrogen atom is 1/12 that. So this is what this means graphically. If you were to set up a balance beam and you were to put 12 hydrogen atoms on one side, that would equal the mass of one carbon-12 atom. Okay? So it's like this is why it's called a relative mass. They did not have the capacity at the time to measure the individual mass of a proton and neutron for a couple of reasons. Number one, they didn't know they existed. Okay? Number two, they hadn't developed the capacity of electric and magnetic fields to do like the experiment like you did on the last test where you shoot it through an electric and magnetic field, and then you shoot it into a magnetic field, and it curves, and you can figure out the mass of the particle. They didn't have the capacity. They said, hey, look, close enough. Let's just call this what it is. We're just going to go off relative atomic mass. What they figured out later on, and this is one of the quirky things that we got very lucky on, is that once they figured out that there were protons and neutrons, and then for rough estimates, they said, oh, each neutron and proton has a relative atomic mass of about 1. And again, until they revised the capacity to exactly measure those values, everybody was good with that. Oh, let's just call it 1. Cool, right? Yeah. So what they figured out later on, though, once they developed the technique to measure this to a much higher precision, that the neutron's mass is slightly more than the proton's mass. Not a significant amount.
How did we know that?
There's no we, pal.
They use the proof.
They use scales?
I'm lying to you guys, I'm lying to you. Sorry.
Shit, I was just lying. Never mind.
Okay. So, the other numbers that you're going to need, like for example, if you look at like iron. So if you come over here to iron, okay, and you've got atomic number 26 for iron, and it's got the mass number. You're going to need these numbers. These are, gives that atomic mass. These are very, 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 very precise measurements of these atomic mass values. You have to use this appendix for chapter 30, and I'll show you why. So, if you want to find the amount of energy that's released or that you have to put into it, the basis of this whole idea is Einstein's equation that E equals mc squared. So, M is the amount of mass that's involved in a transition of some nuclear reaction. So, for example, in our sun, you take 4 hydrogen atoms, and this is a very short version of this story, and you change that into a helium, which has an atomic number of 2 and a mass number of 4. So here's the significance of these numbers up here. If you have the 4 hydrogens, and you look at these numbers, the mass of this helium atom here is slightly less than the mass of the hydrogens. There are some other steps involved that involve neutrinos and some other stuff which we'll get into later. But here's the basic idea. The reason that we have this big ball of light in our sky is that hydrogen is turning into helium. And in this process, there's a slight loss of mass. And that slight loss of mass gets plugged into E equals mc squared. Now, C is what? Speed of light. Okay? Speed of light, 3.00 times 10 to the 8th meters per second. And that's going to get squared. So it doesn't take much of a loss of mass to produce a tremendous amount of energy. Now, this is not the mass itself. It's the loss of mass that occurs. So, here's how this would play out. So let's say that you're given this problem, and I'm going to give you all the numbers to save some time. So you've got what you might be asked to find is what's called the binding energy of the isotope iron 56. The binding energy is going to be what would represent how much energy was lost if you take a nucleus and you separate it out. And in other words, you separate all of these particles, and instead of being all one thing, you're going to separate this out. Now, just don't ask any questions. I got to slam through this. So your binding energy, and this will make sense in just a second.
Dude, how much string are you wasting? It's like 3.
He's proving
Oh
string
my
theory, bro.
god.
Big Mike's proving string theory.
You know, I actually tied a string to my hand. You should actually be thinking. You should be thinking.
Okay. So here's how you calculate binding energy. So let me explain what this is. What you do is you take the sum total of all of the mass of the protons and the sum total of all of the mass of the neutrons. Okay? So this is where you have to use this chart on A3. So if you go through this, a typical, all of these iron atoms have 26 protons. So what you're going to do is you're going to take 26 times 1.007825. Okay? And I'm using that because that's the mass of the proton. Now, I've got 26 protons. So how many neutrons do I have? 30. So to that, I'm going to add 30 times the mass of the neutron, which is 1.008665. So that's the total mass of the particles that are locked inside of it. Now, what I do is I subtract from that the mass of the atom.
Don't look at me. I'm playing with this. I didn't touch anything.
So, again, this is just a number that you look up. And that's 55.9439440. Okay? So, the difference between these two is the mass difference between the sum total of the protons and neutrons versus an individual atom. Okay, so in other words, if you're just, hey, I want to build an atom, I'm going to go to the store. I'm going to buy 26 protons and I'm going to buy 26 neutrons. I put this mass of H because what's listed in the book is it doesn't say proton, it says a hydrogen atom. Okay, that's why it says MH. MH is the mass of the single proton, but your book listed as the hydrogen atom. Now, here's the other number that you need. This 931.49 mega electron volts over C squared, which seems random, because there's two ways that you can do this calculation. One option is that you take the difference of this mass that's in atomic mass units, and you convert the atomic mass units into kilograms, which is a whole another conversion. But then you'd have the difference in mass in kilograms, and then you'd multiply it by the speed of light squared. That gets you an answer that's in joules. It's a long process. Or you shortcut it, and you use this handy-dandy conversion, which is 931.49 MeVs over C squared. So what that does is that this, by multiplying it by 931.49, takes the place of doing that whole conversion from atomic mass units into kilograms and multiplying it by the speed of light. Okay? So yeah, so basically you do all this math, and if you do this, you get 492.26 MeVs. Okay? So this is one of the handiest conversions that you can have, because otherwise it is a long slog. What?
Is that even for the easy, like milli or mega?
Yes. Mega electron volt.
So you can put your answer like that?
Yes, exactly. And that's typically how they're given.
Where'd you get the 55 point?
That, if you look at the back, that's the mass of an iron atom.
So will they give us like we total amount of mass?
Yeah, they have to tell you which specific iron atom they use. So this was like iron 56. If it was iron 58, it'd be completely different.
Yeah.
Listen.
Can you go back to the equation with the subscripts?
Okay, so this is Z, which is the number of protons. Okay? Which for iron is always going to be 26. This is the number of neutrons. And that depends upon the isotope. Okay? And then this here, so what you're going to do is take the number of neutrons, multiplied by that mass. This is the mass of a single neutron. This is the mass of a single proton. Right? And then this is the mass of the entire iron atom. So these two numbers here, when you add them together, are bigger than the mass of the single iron atom. So to get it into energy, like I said, there's two things that you could do. You could get this difference, convert it into kilograms, and multiply it by the speed of light squared to get an answer that's in joules. Or you could just use this handy-dandy little conversion of 931.49 MeVs per C squared. It just saves you a whole bunch of hassle. Okay? That's all I'm telling you. It saves you a whole bunch of hassle. Okay, so we'll call it good. Tomorrow we're going to go through different types of decay. And then the last quote assignment over chapter 30, I will give you the answer keys to it. And there you go.
Should we do
tomorrow
it?
We'll finish up radioactive decay.
No homework today?
No homework.
Yes.
I gotta
Study for what? Study for what?
They had a question about that finding.
Calc 1 or Calc 2?